Hey guys, Buildzoid here, and today we're going to be taking a look at another one of my questionable eBay purchases. This time, the Gigabyte X58 G1 Assassin motherboard. So, I picked up this motherboard for a couple reasons. One, it's huge. So, pretty standard EATX thing. It's wider than a ATX motherboard. So that's not, and this really isn't even remotely the widest motherboard I've ever seen. And I'm not referring to like server boards. Like obviously there's those server form factors which are ridiculously wide, like motherboards that are rectangular in the width direction rather than the height direction. Actually, I think there's even some MATX boards that are not quite square, but anyway, so, super wide, like, it's not really that wide, so that's not really the reason that I was interested in it. No, it's really freaking tall, and admittedly, I have a couple other really tall motherboards, but can never have too many of those, as far as I'm concerned. Yeah. ATX ends here, at that screw hole. This monstrosity over here, this is an XL ATX motherboard. It's very tall, it's also pretty wide. It's also not a real form factor, but, it's a sort of catch-all term for everything that's tall and like just bigger, like taller than ATX basically. So anyway, that's part of it, was just like it's a big motherboard, and big motherboards are kind of rare because they're pretty impractical, and like this one's big in like the wrong direction even compared to servers. Actually, I think the SR2 is both super tall and super wide. I can't remember right now. I'll have to check. Anyway, so pretty wacky that it's really tall. Other than that, we've also got, like, this is this is Gigabyte's original take on a gaming motherboard. So we've got fun things like killer networking on board, with its own memory chips, which is not really something you see these days. Like, I can't really think of... Well, the thing is, I don't pay that much attention to networking, so I'm going to assume that networking chips probably have some of their own internal memory. But when have you last seen a networking chip on a motherboard? I'm sure networking cards have memory is built into them as well. Now on a motherboard where you actually have memory chips for the networking chip. So, yeah, that's kind of wacky. Not the wackiest part of this board as far as I'm concerned. We've got a similar thing going on with the audio section here. We've got this memory chip that I can only assume is for the audio codec stuff. I don't really pay attention to onboard audio, so yeah. But that's a thing. It's a high-end old Gigabyte motherboard. Actually, like, Gigabyte's been on top of dual BIOS for, like, years and years and years. So, yeah, it's got dual BIOS. It does not have the switches for it, so this is the super obnoxious variant, which randomly jumps between one BIOS and the other, and the only way you can get it back to the main BIOS is by power cycling the power supply, so very, very cool. Like, Gigabyte, like... I don't know why they came up with this, but it's been around for ages, and it always sucked. Anyway, down here we have a clear CMOS jumper, and an OC button, which, as far as I can tell, all that did was, like, on the fly, change the CPU ratio, I think. Like, it's not super well documented or more like... So I read what that button does, and then I didn't put it in my notes. That's what happened. My notes aren't very well documented as to what that button does. But if I remember researching it correctly, like, it basically was just a turbo button. It would temporarily overclock the CPU. Like, it would overclock the CPU up, which is kind of neat, but it would have been much better if it was just like a plus-minus ratio button or, something actually useful like that. Speaking of things that would be cool if they were actually useful... we've also got a bajillion LEDs on this motherboard, but no postcode, and they aren't RGB. Actually, I don't think there's any blue... no, I think there are some blue LEDs on the board. So technically it does have RGB, but it also has yellow LEDs in a lot of places. So for example, over here, we have LEDs for indicating the frequency of, I believe, the CPU. Basically, they light up more the more you overclock your CPU, so that's neat. We've got LEDs over by the memory to indicate how high your memory voltage is. It goes up to, like, red if your memory voltage is really high. We've got more LEDs down here. I think those are for the... No, I think these are for the... Yeah, so... Wait, South Bridge voltage. Man, this thing's... Yeah, so we've got South Bridge voltage indication. I think... Oh, DDR phases. Yeah, so how many memory phases you have running? I would assume some of these are also North Bridge. Because technically you have, like, the North Bridge has a 2-phase, the memory has a 2-phase. There's 4 LEDs over here. Anyway, so you're kind of getting the idea. We got more LEDs over here, which are for indicating the North Bridge voltage. And we've got LEDs over here for indicating the core voltage and how many... Actually, no, I think the phase count LEDs are somewhere over here. Yeah, I think... Yeah, that's actually the phase LEDs. Okay, so it's CPU frequency, phase count LEDs. Now... There's only 4 LEDs, but this is actually a 16-phase motherboard, and I've just spoiled the big surprise about why the hell I wanted this board. That's the primary reason. We'll get to it. Anyway, so we've got all these LEDs all around the board, but we do not have a postcode. So, yeah, we have all this, like, visual information delivery that's completely freaking useless because there is no bloody postcode. You gotta love these old motherboards. Like, you've got... Like, I don't get it. Like, what is the... Oh, and also there's no voltage read points. Like, you gotta love just, like, priorities. Like, we've got voltage level indication LEDs everywhere, but no voltage read points. We've got a frequency LED indicator, but no freaking postcode. And we've got an OC button that technically changes the CPU ratio, if I remember how it works correctly, but no actual ratio up-down buttons. So, yeah, that's great. That's serious. Like, I get that this is I mean, this basically is exactly what you get on a, like, this is the whole idea of a gaming motherboard, is just look very fancy, don't actually be functional. You know, most well embodied by Strix motherboards these days. With the postcode, and actually those do actually come with a postcode, so that's not too bad. Oh yeah, other than that, we've got Molex power connectors for extra power to the PCIe slots, because there's 4 of them, and if you ran quad GPU, you could very easily melt a 24-pin. That's not really that difficult to do, as 24 pins aren't really designed to handle the load of 4 GPUs. They're not really even designed to handle the load of 3. So yeah, the Molex power connectors for the extra PCIe power. I think one of them might be for, like, audio power or something silly like that. Maybe Northbridge power. But yeah, I'm not going to worry about that too much. Actually, no, it just says PCIe right here, V_1. So I'm guessing this lower one has _2. Yeah, so they're just PCIe power. Why do you need 2 Molexes? Well, I guess Molex is a terrible connector as well, so more is more, and therefore better. Anyway, we've got dual 8-pin power connectors, and this is actually sensible because... the CPUs that you can put into LGA 1366, they might not have a lot of cores, but the thing is, they have... So, LGA's 1366 CPUs have a stock TDP of over 100 watts, very regularly, and they come at frequencies of around 3 gigahertz. They can overclock well into the 4 gigahertz range, and let's put it this way, your power draw increases linearly with your operating frequency. So if you go from 3 gigahertz to 5 gigahertz, that is a 66% increase in power consumption. Before you even consider the power draw increase from the increased operating voltage. Now, 1366 CPUs don't generally go all, like, they need quite, like, you need sub-zero cooling to push them that far, but the point still stands. You do kind of want... more than 300 watts of power delivery available. And on that note, I think also these power connectors use the old folded, yeah, so these are the old folded metal pins, and so these don't even handle as much power as the 8 pins that we regularly see on high-end motherboards these days. So yeah, let's talk about the monstrosity that is the VRM. Though it's not really a monstrosity by today's VRM standards, but... You know, back in the day, achieving a 16-phase VRM of any kind was actually quite difficult. Though, funnily enough, we did have 10-phase and 12-phase voltage controllers back then. Those then fell out of fashion. The 12-phase one wasn't really that great and only ever really used on GPUs. Actually, I'm not sure it wasn't that great, but, like, I suspect it wasn't that great because it isn't really that popular, and that... Now, it did get used on a couple high-end cards. The thing is, the power delivery requirements for older hardware in terms of transient response were a lot lower compared to modern hardware, and so the voltage controller didn't have to be crazy fast, like you would want with some of the modern, like with what, like you'd want for modern CPUs. Anyway, so this is all V-core because this is LGA 1366, and there's no weird, there's no iGPU rail or anything like that. And then for the other rails like the QPI, IOH, so North Bridge, and memory voltage, we've got this over here, that over there, and this over here. So, yeah, anyway, V-core, 16 phases, and it is actually 16 phases. Even though it uses only a 6-phase voltage controller. So we've got an ISL, and it's not even running 6 phases. Of course it's not. This is an ISL 6336G, and the G, as far as I can tell, stands for Gigabyte. So this is a special variant of the ISL 6336 created specifically for Gigabyte, so that Gigabyte could go do very silly things with intersills. I think back then this chip was actually new. ISL 6617 doublers. So yeah, we've got a lot of those on this board. And yeah, like this is literally a variant of the 6336 designed to function with ISL 6617s. I can't find documentation for the 6336 itself or for the 6336G. I can find documentation for the regular variant because I assume this was Gigabyte exclusive, and so yeah, it didn't really show up anywhere else. But 6-phase, and I suspect this chip goes up to 1 megahertz switching frequency max. And I'm basing that off of the fact that this VRM actually runs at 260 kilohertz, which you might be like, isn't that... Well, actually, we should get through the control scheme first before we get into the switching frequencies. So, control scheme, ISL 6617s. On the front of the board, we have 6 of them, right? So, that's all of these. On the back of the board, we've got another 6, because of course we do. Right? There's your 6 doublers on the back, 6 doublers on the front, for 12 doublers in total. So, this achieves this insanely high phase count by doing the following. First, you take 4 phases from your ISL 6336G and you shove it into 4 6617s. And then you take the output of that, which is now 8 phases instead of just 4 phases, and you shove it into 8 6617s. Because of course you do. And then the output of that is finally our 16-phase VRM, which is shoved into these lovely chips, which were very, like, Gigabyte used these a lot for like ages and ages and ages. They have Z68 motherboards with them, P67 motherboards with them. I would assume they probably have some P55 motherboards with them. Hopefully they never used them on an X79 board because they're grossly inadequate for that. They did use them on 990FX boards, which is also not necessarily the best place to use them, but hey. Anyway, so the chips they used are the SiC 769s. And these are just basic DRMOS components. We'll get to the power handling soon enough. Anyway, this control scheme right here. So what's cool about this board is, like, we've got doublers for your doubler. Well, actually, we've got doublers for your voltage controller. And this is a configuration that is actually officially supported by Intersil. Like, Intersil literally, in the documentation of the 6617, they're like, oh yeah, if you want a really stupid phase count, you can go and take your one 6617 and then put 2 more 6617s after it, and then you can go from like 1 phase to 4. And then you can do that with like a 6-phase controller and go up to 24 phases. And Gigabyte has done that, I think, on their Z68 motherboards. And they also had like 20-phase designs on Z and P67, because P67 and Z68 motherboards are basically the same thing. In a lot of cases, yeah, they're basically like, you have a lot of P67 and Z68 motherboards that are basically the same power delivery, same everything. They just swap the chipset. And maybe some minor feature tweaks, but anyway, so Intersil was like, yeah, you can do this. And Gigabyte was like, yes, we can. 16-phase VRM with all of the doublers actually running in interleaving mode. So I went ahead and checked, because the funny thing about the 6617 is if you see an ISL 6617 on a modern motherboard, with all probability, it's actually not running in doubling mode whatsoever. It's probably running in synchronized mode. And the reason why on modern motherboards these are normally run in synchronized mode is because these days you kind of prioritize transient response over input ripple. Over input ripple, because the transient loading of modern hardware is a lot higher than of the older CPUs like you had on 1366. I mean, you can just kind of see that from just looking at like the capacitor configurations on the CPUs themselves. But anyway, so on modern motherboards, if you see a 6617, with all probability, it's just being used for current balancing two phases that are, two power stages that are actually running in phase with each other. So like a great example of this would be the Z590 Dark that uses a I've forgotten the controller, but the controller is putting out 8 phases on that board, and that goes then into a bunch of ISL 6617s, and those 6617s are in synchronized mode. So the Dark has an 8-phase V-core with per power stage current balancing, which gives you really great transient response, but you don't get you get slightly higher input ripple, which you compensate for by just having more input filtering capacitors, which is why these days nobody sort of bothers with the super high phase counts. In fact, even Gigabyte doesn't use 6617s in the phase doubling mode. Honestly, it seems like Intersil eventually came to the conclusion, because a lot of motherboard VRMs are typically designed in collaboration with the actual chip, like the controller manufacturers. So I guess Intersil at some point came to the conclusion that honestly using the doubling mode on the 6617s is just totally bloody pointless, and you can just run them in synchronized mode to get slightly better efficiency than not using doublers at all, but without the downsides of the slower transient response, because that's kind of the main issue with this. And actually, this is even worse because so doing this limits your maximum duty cycle. So one of the features of the ISL 6336 advertises is that it goes up to a 90% duty cycle, which if you were not running any doublers would give you an output voltage of 11 volts or something completely stupid like that. So normally a voltage controller doesn't need to have a crazy high duty cycle as part of its standard operation capabilities. But if you're going to be quadrupling, you need a crazy high duty cycle, because the way these doublers work is basically you send in a signal that is at 1 megahertz and has a really high duty cycle, and then it goes through your first, let's say you wanted 1.2 volts output voltage, right? So you would send 40% duty cycle at 1 megahertz into your 6617s. That would then get turned into 20% at 500 kilohertz on the output of them, but 8 phases. Because basically what the doublers do is they send every other pulse to, that's all they do. Send every other pulse to one of the 2 outputs that they have. So all of the even pulses get sent to the even output, and all of the odd pulses get sent to the odd output. So the frequency gets cut in half, the duty cycle gets cut in half, and this is why the controller needs to be aware that there's doublers there, because if the controller doesn't know you have doublers, your output voltage is going to be super, half of what you're aiming for. If you're quadrupling, like we are on this motherboard, you actually need to send 4 times the duty cycle that you actually want. At the phases. So anyway, that gets cut down to 20%, 500 kilohertz, and at the output we get 10%, 250 kilohertz, which is conveniently enough kind of close to what the motherboard actually runs. So I checked this board with an oscilloscope because I've seen far too many modern motherboards where I didn't check how the phases were actually running. And I'd be like, oh yeah, this is a 12 phase. And then I'd go check it with a oscilloscope later. And it's but none of these are interleaving. You can only measure 6 phases in the VRM. This is actually 16 phases. I went and basically checked one phase against every other phase there is. And they're all out of, or more I checked one inductor against all other inductors. and they're all out of phase with each other. Therefore, this is a 16 phase because none of them are in phase with each other. If you compared it to say like say a Gigabyte Z390 Aorus Pro, that board is a 6-phase that uses ISL 6617. So actually on that board, what you'll see if you take an oscilloscope and start checking how the inductors are being switched, you'll see 2 inductors switching on and off at the same time. So you have 12 inductors in total, but only 6 phases, and 12 power stages, but again, only 6 phases. So anyway, this is an actual 16 phase with quadrupling. What this does for transient response is probably horrendous, and further amplified by the fact that for some reason Gigabyte used insanely high inductance inductors. These things are 1 microhenry, which is huge. Okay, for comparison, modern motherboards normally, with the exception of Asus likes to use really high inductance inductors, probably because they were the first to jump on the whole, hey, let's whack all of the power stages in parallel, but they use those really high inductance inductors even before that, which is kind of weird. Actually, I think I guess they introduced them with X99, and that makes sense, because there you had a fully integrated voltage regulator. Anyway, yeah, normally, if you want good transient response, you want low inductance inductors, because it gives you a higher slew rate, and it reduces how much energy is stored in the inductor when you go from a load to idle transition, which reduces your voltage overshoot. This, on the other hand, is on 1 microhenry inductors, which is like 5 times what you normally see on modern motherboards. Yeah, like these days, say Gigabyte typically uses 150 nanohenries per phase. ASRock normally is somewhere in like the 200 nanohenries per phase range. Asus is at around the 200 nanohenries mark as well, because if you put your power stages and inductors in parallel, it cuts the inductance in half effectively, which is actually sort of the advertised functionality of the synchronous mode of the 6617s is like, hey, you can, on the, like the idea with the whole reason why the 6617s have synchronous mode is that originally when Intersil designed them, they were like, yeah, you could switch on the fly between, doubling and synchronized mode, and you could basically go from having really like lots of phases with high inductance per phase to very few phases with very low inductance per phase and very high current slew rate, so you could get really good transient response and also really good steady state ripple. The bad news is that actually implementing this in terms of the control loop is very difficult, and so I don't think any motherboard actually does that. This maybe does. I've not gotten around to like doing a full load test on the, like, I've not gone through load testing on the motherboard to see if it does anything other than just running the doublers in doubling mode. I'm pretty sure it just runs them in doubling mode, because it's similar to how these days modern motherboards just run them in synchronized mode. It's just it's far easier to just not, do anything weird. So, to not sort of switch between the 2 operating modes, because it totally changes how the VRM behaves. But anyway, so yeah, very high inductance inductors, very high phase count, 2 sets of doublers, so you get more delay on the PWM signals. And then as far as X58 motherboards go, this is not a lot of capacitance. Like, there are X58 motherboards where all of this space that's taken up by inductors on this board is actually occupied by capacitors. And so this board, this VRM, and I've not had a chance to measure it, and I really do want to measure it. Like, this is one of the reasons I picked this board up, is like, because I also have Gigabyte motherboards for X58. Like, I have a lot of X58 motherboards, and basically, if I figure out how to get a piece of coax attached to an X58 CPU, which is actually way harder than it might initially sound, because unlike a lot of the various CPUs that I've modded, like added coax to for modern platforms, they have very convenient places to put coax. Like on a 10700K, which is what I used for my Z490 motherboard testing, there's just a vCore power plane on the very top layer of the CPU, like on the top part of the CPU substrate, and there's also a ground plane. So you just sort of scrape off a bit of the solder mask, and ta-da, you've got like the perfect place to measure vCore. X58 CPUs, not so much. So that's really annoying, though. I think the pinout on them actually works out that you get like a bunch, like I think it's like vCore ground rows in this area. So it might be possible to take advantage of that and just hook up the coax to like two V-core, like a V-core pad and a ground pad of the CPU. Though that, like, I'm not a fan of that because if like the pin contact changes in that area, it's gonna like mess with the measurement. It's the same reason I don't like measuring from the motherboard itself. Is just like I don't know how well the motherboard is designed. Yeah, like I don't know how well whatever measurement point I chose is connected to the CPU, so it's gonna throw off the measurements. But yeah, I'd love to test the transient response on this and compare it against some of the not so doubled lower inductance VRM designs that there are for X58. Because there's quite a few, like there's a lot of variety in terms of VRMs on X58. So yeah, I'm kind of like, if I figure out how to get X58 CPUs probed, that would be really cool to do. And this motherboard will probably suck. But that's part of the reason I bought it. It was cheap. It came with an i7-920, which honestly isn't really much of a value add, but there we get a funky VRM to look at. Now, as much as I've been bashing on this for too many doublers, too much inductance, not enough capacitors, it is actually, in terms of current handling capacity, very capable. Because the SIC 769s are 35 amp DRMOS components, which doesn't really sound that great, but unlike, say, your 70 amp smart power stages, you can realistically kind of cool 35 amps going through a 35 amp DRMOS component. You can't cool 70 amps going through a 70 amp component. Like, not practically. Technically, yes, but realistically, no. These, on the other hand, when you load them up to 35 amps, just don't, like, ultimately in this configuration, you still wouldn't want to do it because Gigabyte put a grand total of 4 power stages on the back of the board, and no, there isn't some fancy backplate heatsink, they're just kind of there. And Gigabyte gets away with this on this motherboard because, like, they have 16 35 amp DRMOS components. This VRM is actually pretty good in terms of efficiency. It probably is absolutely horrendous at voltage regulation, especially compared to, say, something like an X58 classified or a Gigabyte X58-OC. But yeah, in terms of efficiency, this is not bad. In fact, I think this technically has more current handling capacity than the X58-OC. Because if I remember correctly, the X58-OC board from Gigabyte is a 12-phase using the exact same power stages. So yeah, because Gigabyte evidently bought like a warehouse full of these and they just put them everywhere. Anyway, let's talk about the actual power delivery. So, I mean, yeah, power delivery capabilities. So 1.2 volts output voltage, 300 kilohertz switching frequency, which is actually above what this motherboard runs. And it's also worth noting that this really high inductance actually, like, that helps reduce the power losses in the power stages because it reduces the RMS current flowing through the power stage. So, like, really, this VRM basically looks like this. This, on paper, is really high efficiency relative to what was available at the time. Obviously, modern power stages in terms of peak efficiency blow this out of the water, but at the time, really high efficiency, probably great. It like steady state, like a steady state, it should perform really well. And then on load transitions, I have no idea how this deals with them. Probably not well. Luckily, a lot of benchmarks like Cinebench don't really have a lot of load transitions, but I imagine something really noisy like Linpack would probably not go very well with this VRM. So, yeah, anyway, that's kind of the fun, which is probably part of why, like, well, Gigabyte does have, no, because Gigabyte on the UD7, no, UD9, so, yeah, I guess that's why this VRM is on a gaming board, because if you look at the mainline, like, more overclocking-focused motherboards from Gigabyte, I don't think any of them have cascaded doublers like this, now that I think of it. Because the UD9, I think, uses, like, 2 controllers somehow working in parallel. I need to get my hands on that board because I have no idea how that works, and that's really cool. But anyway, so high inductance does improve efficiency. Also, the VRM on this board, when I measured it, runs at 260 kilohertz, which you might be like, isn't that technically like 1040 kilohertz at the actual VRM, so how could this be a 1 megahertz controller? There's quite a lot of tolerance on the switching frequency. Like this, the switching frequency of a VRM is not a super tightly, like plus minus 10 kilohertz is like, whatever. Like a lot of modern motherboards, if you set them to like 800 kilohertz, they end up at like 880 or something. I think I've had a few boards like that. And also I had one board where I think at 1 megahertz in the BIOS, it was like 900 kilohertz IRL. And so, yeah, there's a lot of tolerance on the switching frequency. It's just not really a priority. As long as you're roughly what within 10% of what you were aiming for, you're fine. That's basically what goes on with the switching frequency. So measuring 260 kilohertz to me is like, yeah, this is a 1 megahertz controller probably. Anyway, let's talk about that power handling capacity, since I've been sort of tangenting away from it for a while now. 100 amps output, this should produce about 10 watts of heat, which is good. It's not like, I've seen there are VRMs that can do better than that, but that's honestly not bad. 200 amps output, it'll produce about 22 watts of heat, which is also not bad. I mean, again, on modern motherboards, I would be expecting like, hey, 14 watts of heat at 200 amps with 1.2 volts at 400 kilohertz, not 300 kilohertz. But back in the day, this is great compared to some of the old motherboards that I've done PCB breakdowns for, because yeah, MOSFETs have gotten a lot better, and power stages got a way better too. Like basically the 70 amp smart power stages are like a whole another performance class above the old, like, well, no, so Intersil actually had the 99227B before the 70 amp parts started coming out, and that already has like the same efficiency curve as the 70 amp stuff does. Yeah, back in the day, like the 60 amp power stages I don't think even existed. So this was this is great. Today it would be kind of like, but yeah, for an old motherboard like this, I'm impressed. 200 amps while only producing 22 watts of heat, that's really freaking good. 300 amps output, it'll produce about 40 watts of heat, which still isn't bad for such an old board. And you also have to consider the fact that all of that heat is spread across 16 power stages. So yeah, in terms of like cooling, and the board does have pretty substantial heat sinks. In terms of cooling, this is not too bad. Also, 300 amps going into at this point, because these are relatively high voltage CPUs, like, I think to hit this level of current draw on a 1366 CPU, you'd probably be looking at around 450 to maybe 500 watts of total CPU power draw, which is LN2 overclocking territory. So you're probably not going to be running that level of load for very long. And 400 amps output, it'll be producing about 68 watts of heat. Which, I mean, honestly, like, still not bad by old motherboard standards. Like, it's a lot. And honestly, I think at that point, like, if you actually wanted to run 400 amps on this VRM for any sustained amount of time, you would definitely have to do something about these power stages on the back. But also, I'm not entirely sure that you could hit this level of current draw for, like, sustained loads on X58 in the first place. So it kind of doesn't matter. This sort of tends to, like, when it comes to motherboards, that 400 amp figure, with the exception of like Threadripper boards, is more of a, academic sort of like, what would happen if you did something insane to, like, if you could run higher power draw CPUs than realistically go into the socket. Yeah, so very powerful VRM. Just in terms of the control scheme and then the filtering, I'm kind of like, this probably sucks at transient response. I say probably because, again, I've not measured it, and until you measure something, you don't know. But everything I'm looking at here to me is like I have literally measurements of a motherboard with both like low inductance and high inductance inductors, and high inductance inductors make your transient response worse. Who could have expected that? Less capacitance is bad. Low switching frequencies don't necessarily actually do anything, funnily enough. But that more depends on how the controller works than the switching frequency itself. So on this older controller, the low switching frequency might actually be, well, it's 1 megahertz at the controller, so it might not be that much of a problem. And then the doublers, yeah, they do add some delay, and when you double that delay by putting 2 sets of doublers, probably becomes kind of an issue. So yeah, that's the VCore VRM. And then for the other VRMs, we've got this right here, which Gigabyte calls this rail VTT, I guess. Okay, so that's QPI. Yeah, and now this one, you might be looking at this and it's like, oh, that's a 3-phase. No, it's not. If we look at the back of the board, I'll see if I can make sense of this. Where is that rail? Ah, there we go. So you've got a phase, you got a phase input filtering inductor. So basically, and you can see this also on the VCore VRM, like there's this inductor hanging out by the power connectors right here. So all this inductor does is basically block all of the switching noise from the VRM from passing on to the PSU. Like basically on this side you see a lot of switching noise, on this side you see less switching noise, thanks to the inductor. That's what it's there for. It also reduces the transient loading on the power supply as well. So if you have a really, which basically just looks like a really big voltage spike instead of a small voltage spike. So, and actually it would be more like a really big voltage drop rather than a spike. But, you know, like if you have a short voltage drop, it's just a spike downwards. So still a spike. Anyway, so yeah, input filtering inductors are basically just to block the switching noise from the VRM from going to other parts of the system. So that's the same idea, because like this doesn't run off of the 8-pin power connectors. I don't think this runs off of like the 24-pin. And you can see that we have an input filtering inductor for the memory, input filtering inductor over here for the chipset rail maybe? No, this has to be Northbridge. Yeah, because QPI is the memory controller, and then this would be Northbridge. So unfortunately, I don't know that much about X58. But yeah, so basically the input filtering inductors are there so that like the switching noise from this VRM doesn't affect this VRM, because I'm pretty sure they share the same power rail. And anyway, so yeah, we've got the QPI/VTT rail. And the reason I use the term, like a lot of people call it VTT, I call it QPI because VTT DDR is a totally different thing and not to be confused with VTT. Whereas QPI makes much more sense to me because these CPUs had a QPI link that sort of runs on this voltage right here. And it also powers the memory controller. Like this is basically system agent. So yeah, you can sort of think of this as a system agent rail. Anyway, so we've got 2 phases and 1 input filtering inductor. So as much as it looks like a 3-phase, it is not a 3-phase. And then for the MOSFETs, I have completely forgotten how this is laid out because it is whack. I think it goes high, low, and then on the back, we do have more MOSFETs. So I'm guessing, yeah, I think high, low, and I think it's grouped like this. Yeah, I think it's grouped like that. Anyway, doesn't really matter. If it mattered, my notes would have actually sort of tried to account for that. And the reason it doesn't matter is because Gigabyte used the exact same MOSFETs for all of these MOSFETs. These are all the same MOSFET. These are all from NEC without the K. This is an electronics manufacturer. I think they got bought up by someone or like merged with someone. Anyway, yeah, NEC, and these are A2724s. And Gigabyte just slapped these everywhere on the board. Like we've got more of them over here, got more of them over here. They're not doing anything wacky over here. You just have like a nice simple high-low configuration. Actually, this might be high here and low there. I'm not sure. Doesn't really matter. They're all the same MOSFETs. Like normally the reason why you make a distinction between the high side FET and the low side FET is because if you're switching, if you're doing a conversion from like 12 volts to 1.2 volts, you want to optimize your high side MOSFET for really low switching losses, and you want to optimize your low side MOSFET for really low conduction losses, because the high side MOSFET is turned on for very short periods of time, whereas the low side MOSFET is turned on like 90% of the time and handling the vast majority of the current, so it needs to be very low resistance. However, Gigabyte is actually running this rail over here off of, I believe, 6.3 off of the 5 volt rail. Yeah, sure looks like it, because we've got these 6.3 volt capacitors over here, as well as over here. And then we have 2.5 volt capacitors right there. And honestly, we've just kind of got a mishmash of capacitors everywhere. But it's pretty, memory definitely runs off of 5 volts. And the reason why you would use the 5 volt rail for these minor power rails is because now you can use, the duty cycle is longer, right? Because if you're converting from 5 volts to 1.2 volts or whatever, you don't need as short a duty cycle as you do when you're converting from 12 volts to 1.2 volts. Because 12 volts to 1.2 volts is like 10%, whereas 5 volts to 1.2 volts is like 20-something percent, more than that. It's like 25% or something. So since you have these longer duty cycles, you're sharing the load between the MOSFETs more evenly, so you can have more similar MOSFETs, or exactly the same MOSFETs, and it doesn't cause the same kinds of issues as if you were if you had a really big voltage step. So yeah, we've got these 82724s, and these are actually really low RDS on MOSFETs. These are like 3.3 milliohms. Actually, we're just going to use the ohm symbol. 3.3 milliohm RDS on, and yeah, that's pretty good. I didn't bother to do the calculations because I don't care enough. The only part of this motherboard I found really all that interesting is this right here, and then everything else is just kind of well, it comes with it. So may as well talk about it. Anyway, this right here is controlled by an ISL 6312. And this is a two-phase controller. Yeah, that's a two-phase controller with built-in drivers and everything, which is why we don't see any extra memory, any extra chips around these for providing the gate drive to the MOSFETs, because that's just built into the ISL 6312. Then for the North Bridge, we've got this over here, controlled by this chip, which that is an ISL 6322. G variant, so I guess Gigabyte special again. Yeah, that uses more of the same MOSFETs, except this time there's just a high and a low and a... Wait a minute, no. So you're going to have a low up there, because it doesn't make sense for it to be... You could have something like that. You could also have a layout that looks like this. I'm not sure. Again, didn't bother to check. Doesn't really matter that much. But yeah, it's just using more of those same NEC A2724 3.3 milliohm RDS on MOSFETs. I guess the noteworthy difference here is this is a lower power rail, so we just have one low side MOSFET and one high side MOSFET in each phase, whereas here we have a total of 8 MOSFETs, right? And so you have 2 high sides and 2 low sides for each of the phases. And the reason you do this is by putting your high side and low side MOSFETs in parallel, you get the RDS on to effectively be lower, which reduces the power losses and also spreads the heat around more components. So you can handle, so this'll, on paper, well, not necessarily, because these MOSFETs are all sandwiched together, so the heat density is pretty high, but this can handle more current than this can, because this just has more MOSFETs in it, even though the phase count is the same and the MOSFETs are also the same. And then the memory power delivery, we're looking at more of the same, just high side, low side, no extra MOSFETs in that, right? If we look at the back of the board, there's nothing here because it's memory. Memory doesn't pull that much power. And that's also controlled by an ISL 6322G located over here. And that handles that. And that is quite a distance between the controller and the VRM, but they ran out of space in this area of the board, so yeah. Anyway, so that's the Gigabyte G1 X58 G1 Assassin. It's green. It has really cringy heat sinks. Seriously, like the heatsinks on this board are quite something. They're not quite as bad as the minigun heatsink on the X79 Big Bang X Power from MSI, but yeah, this is where MSI got the inspiration. And then like turned it up to 11. But yeah, so mostly like big wacky board with really wacky VRM. I really need to figure out how to get proper like voltage measurements off of X58 CPUs. Cause like I really want to do a comparison between this and like the X58 OC board from Gigabyte, which I have one of those. And I also have an X58 classified. And yeah, so I'd love to run like a comparison between all these different VRM designs. Because back in the day, we had a lot more variety. Whereas on modern motherboards, it's all just like, oh, look, it's an intersil controller with intersil 90 amp power stages. We've never seen this before. Except for the part where it's like every motherboard these days, this is the same thing. So, and they consequently, they all perform very similarly. Whereas, you know, on X58, I think like this is a very different VRM than what you see on a lot of the other X58 boards. So, I imagine we should see some pretty drastic performance differences, or at least that's what I'm hoping for. If it performs the same, I'm going to be very upset. That would be really boring. It's just like, okay, so apparently you can just end up at the same, like, it's true that you can end up at the same conclusion using a variety of different methods, but like, you know, like, I'd like to see the VRM design actually kind of matter somewhat. And I think X58, or, well, to be fair, there was an Z370 motherboard that I tested, which was absolutely bloody terrible. So I guess there is variety. It's just that you need to go like digging through the low end to find it. And that's not very fun. Whereas on X58, we have a lot of different approaches to high-end VRM designs instead of who can cut the most corners before it stops functioning, which is what you get on low-end motherboards of any chipset, right? So, yeah, anyway, that is it for the video. Thank you for watching. Oops, why is this not working? I wanted to zoom out a bit. Yeah. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There is a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. And what else was there? Right. Patreon and Teespring help out immensely with running the channel. How do you think I fund all of these questionable eBay purchases? Yeah, I guess maybe if you don't want to fund my hardware addiction, then I don't use Patreon. But if you want to see more weird motherboards like this, or more like wacky motherboards, it's not really that weird. It's just wacky. Isn't that basically the same thing? Anyway, I'm getting distracted. Yeah, much appreciated if you support me through Patreon or Teespring. And that is it for the video. So thanks for watching and goodbye.